Okay, what I want to talk today about is functors. The three sort of main ones that we're going to use in this course, which are map, filter, and fold. So what these do is they're typically going to be done on lists. So we're going to mostly focus on lists here, but they essentially are formal ways to apply a function onto a bunch of copies of data or different parts of data. Right, so for instance, if we have a list, right, of say 1, 3, 5, 7, and I want to apply some function, right, so maybe I have some function f, which on an integer, what does it do? Maybe it just multiplies n by 2. This pen's a little weird as well. And suppose I want to apply f to every element of this list, right? Well, the standard way that you probably are used to doing it is to have a for loop that's going to run through my list. And for each element of my list, I apply f, and then I append that element onto a new list and return that new list. Map lets us avoid doing all of that simply by, well, let's give this a name. Val L is going to be this list. And all I do is say l.map f. And what that does is it applies f to every single element here. And returns a new function, so a new list, which is going to be, right, double everything, so it's 2, 6, 10, 14, right, and this will be L new, which is equal to L.map f. Right, you could ask why would we prefer to do this over the for loop? Well, the for loop is a big block of code that you have to manage everything yourself. You have to manage all the list operations. And it's not quite as obvious as to what you're doing as just say l.map f, right? This really easily says do f to every single element of my list and give you back a new list. So readability, once you understand what this syntax means, I think it has better readability than the for loop or while loop. Furthermore, it's more optimized, right? The other one you're dealing with programmer level list management. The map function can be optimized at a lower level since it already knows that what it's doing is taking in a list and spitting out a new list. Further, if you have parallel architecture, right? I mean, even right now, all of our CPUs have typically at least 4 CPUs. Each one of these operations of f can be given to a different CPU, so they can all be done at the same time, and then all of their results concatenated together. So map is really good for concurrency. So concurrency or parallelization. Probably too many L's in there. So it's good for this. And it's more readable. That's in quotes because I think that probably depends on your preference for functors or not. But honestly, I think map, once you know, map does the thing that you fed it whatever you want, or to every element of your list. I think it's pretty straightforward. Now, I've already talked about anonymous functions in Scala, so we can use those as well, right? So we can really say just that l.map, and then we can pop in an anonymous function here. Let's say that it takes x, and then it does whatever we want to it. So if we want to reproduce this f functor, or this f function, we can just do 2 times x, right? And this is equivalent to defining f first and then running map with that f in there. Just that we don't always need to name everything. And with functors, it's usually really nice to say this because it's really clear, at least in my opinion, what's going on here, right? We take L, and for every element of L, we apply this function to it. Done. All right, so map does something to every element of the list. What does filter do? right? Filter is going to apply a function that has to return a Boolean to every element of the list, and then it will only return those which return true. So we could check, let's do something a little more interesting. Um, I need a new list that's more useful than the one that we have. So let's do a list like this. L is going to be the list of 1, 2, 3, 4. It's just going to be the first 6 elements, or 8 elements of the natural numbers. All right, and then I'm going to make a new function. Let's call this is even. All right, it takes in a number and returns a bool. And what does it do? It just checks if, right, and mod 2 is equal to 0, then return true, else false. Right, and now we can say lnew dot filter, or sorry, l dot filter. Lnew will be our name for it. And we just pop is even in here. And what is it going to do? It's going to run through every element of L, and it's going to check, is it even or not? And so if we check what lnew is, it's going to be the list of all the even numbers. Again, we can do a anonymous function here if we wanted to as well, right? Something just like anonymous functions can be fairly complex. One more bracket in there. Right, and so filter is useful if you want to get rid of certain elements of your list or to do stuff beforehand, right? So we can even do filter first and then apply a map to it so that we only do the map onto things that are valid for the mapping function, right? Filter can remove anything that's invalid. The last one I want to talk about is fold. We're going to talk about fold left. And this one's a little more complex, right? The other two just took a single function that it then applied to everything, right? The output was a little different. Map gave you an entire array list with every element with the function applied. Filter gives you the original elements back, but only the ones that pass the filter. Fold left is an accumulator function, right? So this is more like the Fibonacci sequence that we saw, or the factorial function that we saw. Where fold left, it's in this form. It takes an accumulator, and it takes a function, and we apply it on a list. And what does it do? It the function has to be of the form accumulator. Say it's a integer, and then an element, which is say also an integer, and it needs to return whatever the accumulator is. All right, so f has to take in two parameters. It takes in the current accumulator and the element, and then it spits out an updated accumulator. This is the starting accumulator. And obviously that's just the function. But do notice that there's the two parentheses there. This is called currying, and it's a style of having a two-argument function where each function is actually of a single argument. But we'll get into that in a future lecture. Okay, so yeah, what does this do? Let's see. Let's do the summation, right? So let's say f is going to be sum. And so what does it do? It's going to take the accumulator. This is the current sum so far, and the element, and we're just going to pass back accumulator plus element. And so now if we take, let's say, L is going to be, again, let's just say 1, 2, 3, 4. And if we apply L dot fold left on 0 and sum, what's going to happen? Okay, first thing that's going to happen is that sum is going to get called on 0 and 1, right? It starts on the left. This is why it's called fold left. And it eats its way through all of the elements left to right. So first it calls sum 0, 1, which as we see here, all we do is add those two numbers together. That gives us a 1. That updates our accumulator so that the next call is going to be sum of 1. We can put the parentheses in there. 0, 1, sum of 1, 2. Right, and again, we add the sum, takes these two numbers and adds them together and gives us back that number, which becomes the new accumulator. So we end up having, the next call is sum of 3, 3, right? We add those two together, that becomes a new accumulator. So we have sum of 6, 4. And that's what we finally return, is the final return is going to be 10. So fold left takes an accumulator, that's the starting point, and then applies this function to each element in turn with the new updated accumulator as the next thing to be passed in. So this lets us take a complicated expression or take a list and be able to sort of pull out elements of it. It's called folding because, right, we're sort of compressing this list from a single list down into a single number, or it depends on how we want to use it, right? It's actually quite powerful when you start to think about complex ways to use this accumulator. Because the accumulator doesn't have to just be a number. It can be a more complicated data structure that might track a lot of information that's going through as you do this list. We'll see a couple of examples in the Scala notebook associated with this. But the key idea here to take away is that, yeah, we have an accumulator on the left, and this function takes the accumulator on the left and an element on the right and combines those in some way to give you a new accumulator and basically cuts off the elements as we go, right? And so we start out with sort of a 0. If my accumulator list is up here, we match 0 and 1. That gives us a new 1, right? We match 1 and 2. That gives us a 3. 3 and 3, that gives us a 6. The 6 and 4, that gives us a 10, right? That's the process that's going through here. There's also a Scala functor called fold right, and this one, the function and the accumulator are in opposite order, which feels maybe a little weird until you realize that what is this trying to do? It's going to fold from the right to the left. So the accumulator is the thing that is always on the rightmost point, and that we feed into f, right? And then f gives us a new accumulator while removing the last element of the list. And so we work our way from right to left, and the accumulator just sort of keeps absorbing, according to the rules that f gives us, the elements of the list. Just like fold left, we start on the left, and the accumulator keeps on accumulating, collecting, folding in aspects of the list according to what f tells us, or according to how f is defined. And these three together allow you to do a lot of powerful work. This is, if you've heard of Hadoop, or a lot of the stuff behind fold reduce. What is it? Map reduce. These are all basically large data operators. So the idea is that I can take a database and take, a column in my database that's essentially a large list. I can sort of view it lazily, so I might not have access to every element all at the same time, or maybe it'll be a stream that updates. And I can apply these maps and these fold lefts and these filters in order to get down to the data that I care about, right? I want to remove everything that doesn't have value in a certain field, and then I want to accumulate all of the heights of all the passengers so that I can get the average height, right? So that would be maybe a map to turn heights from centimeters into foots and inches, and then a list, and then a filter to remove anything that doesn't have a height associated with it, and then a fold left to finally do the average, right? These are sort of stereotypical uses of these tools. But they're very powerful, and this style of writing things, right, with a period ends up being, you see this a ton in JavaScript as well, and in sort of callback functions, right, where you end up taking some data and then you apply a bunch of different things to it, each of which has its own definition, but right, you basically can say map f, and then I'm going to map bar on after that, and then I'm going to filter according to foo, right, and then finally I'm going to fold left with some accumulator on my final function. Right, and that would be a classic way to sort of see a computation and to break a computation on a list into a series of easily digestible and understandable applications of functions.